Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Stress and Strain at Heterointerface from the paper Physics at Nanoscale. So the learning objectives of this module are: first, we will discuss the heterostructure with mismatched lattice. Second, we'll discuss about the stress tensor. Thirdly, we will discuss about the stress-induced polarization in semiconductor heterostructure. So students, let us start with a basic introduction about the module. The simplest description of a bulk crystalline semiconductor is that it exhibits perfect or nearly perfect translational symmetry. In other words, suitable translations of the basic unit cell of a crystal restores the crystal back into itself. Implicit in this definition is the assumption that the atoms within the crystal are regularly spaced throughout the entire bulk sample. So this assumption is generally true for bulk materials. However, two important exceptions can arise. The first is that a bulk crystal can include impurities and dislocations such that the perfect periodicity of the material is disrupted locally. And secondly, the crystal can still retain its overall highly ordered structure, yet contain local regions in which perfect periodicity is disrupted either by impurities or dislocations. So these impurities and dislocations can significantly affect the properties of the material. The second situation arises in a multi-layered structures. So crystal growth technology has enabled the growth of thin layers of heterogeneous semiconductor materials called heterostructures. So using exacting crystal growth procedures, the heterostructures can be grown with atomic layer precision. So a very thin layer of material can be grown on the top of, or it is sandwiched between the layers grown with different type of semiconductor material, even materials in which the lattice constant is different. So strain, here comes the concept, and it is nothing but a measure of the change in the length of a material undergoing small deformations arising from an applied force per unit area. This applied force per unit area is called as a stress. The stress and strain, they are generally represented as tensor quantities. These tensors, they have 9 components that describe the relative stress and the strain along the principal direction of the crystal on the planes that are described with normal vectors lying along these principal directions. Heterostructure with mismatched lattice. When a thin layer of material is grown on a different semiconductor, there arises two different situations: lattice matching, which is shown in the figure on the left hand side. That is, if the lattice constants of both the semiconductors are same. Now, next is the lattice mismatching. If the lattice constants of both the semiconductors are different, as shown in the figure on the right hand side. This figure shows a kind of heterostructure where a top thin epitaxial layer strained to adjust its lattice constant to the underlying semiconductor. So in the case of lattice mismatched heterostructure, the epitaxial layer that has a significantly different lattice constant will be forced to adjust its lattice constant of the bottom layer if the lattice mismatch is less than about 10%. So when the top epitaxial layer adopts the lattice constant of the bottom layer, it becomes strained. That is, it is either compressed or expanded from its usual lattice structure in bulk. So there exists a maximum thickness of the thin layer below which the lattice mismatch can be accommodated through strain, as evident from this figure. So there is a critical thickness that is indicated by LC. For layer thickness above the critical thickness, the lattice mismatch cannot be accommodated through strain, resulting in dislocations at the heterointerface. When the thickness of the top layer is less than the critical thickness, the strained layer can be in either compressive or tensile strain, which is homogeneous within the layer. So if the lattice constant of the top layer is less than that of underlying layer, the heterostructure will be in tensile strain, and if the lattice constant of the strained layer is greater than that of the underlying layer, the heterostructure will be in compressive strain. Stress tensor. Now strain is a measure of the change in the length due to small deformations caused by an applied force per unit area known as stress. The stress and strain are tensor quantities which have 9 components that describe the relative stress and strain along the principal directions of the crystal. So the stress vector Pn acting at a point P on a surface with unit normal vector n is defined as Pn vector equal to limit a tends to 0 capital F by capital A, where F is the force and A is the area of the surface. So the stress vector can be written as Pn equal to sigma n vector, where n is the stress tensor and n is the normal vector, and by expanding the above equation we get P1 equal to sigma 1 1 E1 cap plus sigma 1 2 E2 cap plus sigma 1 3 E3 cap. P2 is equal to sigma 2 1 E1 cap plus sigma 2 2 E2 cap plus sigma 2 3 E3 cap. And the P3 component is given by sigma 3 1 E1 cap plus sigma 3 2 E2 cap plus sigma 3 3 E3 cap. So, the relation between the stress tensor and the strain tensor, before discussing this relation, students, here E1, E2 and E3 cap, these are the 3 normal vectors to the ordinate planes. So in the case of cubic symmetry, general coordinates E1, E2 and E3 are the vectors along x, y and z directions. P1 represents the stress vector acting on the surface, whose outward normal vector is E1, and P1 has three components: sigma 11, sigma 12 and sigma 13. Sigma 11 is the normal component and sigma 12 and 13 are the tangential components of the stress vector. Now here sigma 12 is the stress along the E1 direction acting on the plane with a normal vector parallel to the E2 axis. Therefore, in this case, sigma 12, the stress is tangential to the surface of the plane and is called as shear stress. Now, the stress component sigma 11 is the normal component of the stress on the 2-3 plane and is called as normal stress. If the normal stress is positive, acting outward from the surface, it is called a tensile stress. If the normal stress is negative, acting inward towards the surface, it is called as compressive stress. So now let us come back to the relation between the stress tensor sigma ij and the strain tensor epsilon kl, which is given as sigma ij equal to Cij kl epsilon kl, where the index I indicates the direction of the component of the force per unit area on a plane whose normal is parallel to the Ej direction.Cijkl is the elasticity tensor, which can be simplified by some inherent symmetries that reduce the number of independent components of C. So the component of the elasticity tensor must obey thatCijkl should be equal to Cjikl, it should be equal toCijlk, and it is equal to Cjilk. So when a unit volume element is reversibly deformed by differential strain increment d epsilon ij, is then dw equal to sigma ij multiplied by d epsilon ij equal to Cijkl multiplied by epsilon kl multiplied by d epsilon ij. So for an isothermal system, this dw equal to df and this df is equal to Cijkl multiplied by epsilon kl multiplied by d epsilon ij, and we get that del square f with respect to del ij del epsilon kl equal to del square f with respect to del epsilon kl del epsilon ij. Now here we have used that Cijkl must be equal to Cklij, implies that C is symmetric along the diagonal. Sigma ij and epsilon ij have 9 elements each, that's Cijkl must then be 9 cross 9. So the multiplication is then between C, that is a 9 cross 9 matrix as shown over here, and epsilon, a 9 cross 1 matrix, to form sigma, a 9 cross 1 matrix as it is shown over here. So this shows the multiplication of the two matrices. Now since Ij equal to KL, so we can replace Ij by M and KL by N. So for a material with cubic symmetry, the system is invariant under a rotation by 90 degree about the cubic axis. As a result, only three independent components remain of the original 81 elements of C for the cubic case. These are C11, C12 and C44, which are equal to C11 equal to C 4 times 1 equal to C 4 times 2 equal to C 4 times 3, and C12 is C1122 equal to C1133 equal to C2233, and C44 is equal to C1212 equal to C2323 equal to C3131. Now with these simplifications, the elastic constant matrix C for a cubical material becomes as shown in this, that is CMN is of this form. Based on this analysis of stress and strain, the origin of strain-induced piezoelectricity can be understood in heterostructures and how these fields can potentially be utilized in heterostructure-based devices. Stress-induced polarization in semiconductor heterostructure. A polarization field can be produced within a material when a stress is applied to it. This is known as direct piezoelectric effect and can be expressed mathematically as Pi is equal to Dijk sigma Jk, where the components of D are called as the piezoelectric moduli. So the above equation implies that each component of P depends upon all the components of sigma. So Pi given by this equation can be expanded as, that is, we varies the ijk from 1 to 3 and summing all those combinations. So similar equations can be written for P2 and P3. So using the repeated index notation, it can be written in a much simpler and compact form as P1 is equal to D1jk sigma jk, where as usual there is an implied sum over both the indices j and k on the right hand side. It is useful to relate the polarization field P to the strain epsilon. So in the matrix form, P can be written as P is equal to D multiplied by sigma equal to D multiplied by C epsilon equal to E epsilon, which is in the component form, that is P1 is equal to Dijk Cjk Lm epsilon Lm equal to EILM epsilon Lm. Now it is clear from this figure that the properties of the crystal is different along the z-axis than along in the plane axis x and y. So students, as you can see in this figure, which shows a word-side unit cell showing the hexagonal symmetry of the system. Now here the z-axis direction is known as c-axis and xy plane is known as the basal plane. So the lattice constant along the z-axis c and in plane A are generally different. The strains along the z-axis and in plane, they are defined as epsilon zz equal to C minus C naught by C naught and epsilon xx equal to epsilon yy equal to A minus A naught by A naught, where C naught and A naught are the lattice constants in the unstrained system and C and A are the lattice constants under the strained conditions. The piezoelectrically induced polarization field in the z direction is given by Pz is equal to E33 epsilon zz plus E31 epsilon xx plus epsilon yy. So the strain caused by compression or expansion of the crystalline lattice from its unstrained condition leads to either ions together or pulls them apart. In either case, the local dipole moments are different, resulting in a change in the macroscopic polarization vector P. So the figure over here shows a thin layer of aluminium nitride sandwiched between the two GaN layers due to the lattice mismatch between aluminium nitride and GaN. The aluminium nitride layer is strained, resulting in strain-induced polarization fields along the Z direction. So this shows a three-layer system, and here the lattice mismatch of the system is accommodated by straining the thin aluminium nitride layer. And the thickness of aluminium nitride layer should be less than the critical thickness, which for aluminium nitride is about 3 nanometer. A polarization field P is produced along the Z direction. So now one can define the electric displacement vector D, which is given by D is equal to epsilon naught E plus P, where epsilon naught is the free space dielectric constant and D vector can be obtained from Poisson's equation, that is delta dot D is equal to rho, where rho is the charge concentration. So now this equation can be modified as putting the value of D, del dot epsilon naught E plus P equal to rho. Rearranging this equation and defining the polarization charge rho Pz yields del dot epsilon naught E is equal to rho minus del dot P, which is equal to rho plus rho Pz. So the polarization P vector can be obtained from del dot P is equal to minus rho Pz. As the strain condition changes abruptly at the two heterointerfaces in GaN, aluminium nitride GaN structure, the polarization vector changes across the interface. So this equation implies that there exists a polarization charge at the interface. One side of the heterointerface has a positive charge, while an equal but opposite negative charge is produced on the other side. Now this figure shows, that is the figure A, the left hand side figure shows the L-GaN GaN based heterostructure with metallic Schottky contact to L-GaN layer. And the second figure shows the energy band profile of the heterostructure with triangular quantum well at GAN-LGAN interface. And lastly, we have a charge density at the interface. So, the strain-induced polarization field can be used to change the local carrier concentration near the hetero interface. In this system, a Schottky metal gate contact is formed on the top of a thin L-GAN-GAN heterostructure, and the thin L-GAN-GAN structure strained, resulting a polarization field which induces a polarization density sigma Pz at both the interfaces of L-GAN layer. So the polarization charge density at each interface is compensated by the charge density in the top metal Schottky barrier and in the bottom GAN layer. Group third nitride semiconductors exhibit spontaneous polarization due to non-ideality of the crystalline structure. C by A ratio deviates from its ideal value, resulting the difference in the bond length and dipole moment charge. Now, when the spontaneous polarization is aligned, the net polarization is given by P is equal to P Pz plus P spontaneous. So the combined action of piezoelectric and the spontaneous polarization field can be used to change the free carrier concentration. So students, let us summarize what we have learned in this module. First, we discussed about the critical thickness. So when the thickness of the top layer is less than the critical thickness, the strained layer can be in either compressive or the tensile strain, which is homogeneous within the layer. Secondly, the stress and the strain tensors were discussed, and they have 9 components that describe the relative stress and strain along the principal directions of the crystal. Next, we discussed about the mathematical description of direct piezoelectric effect leading to stress-induced polarization, where polarization field can be produced within a material when a stress is applied to it. Next, we discussed about the strain which can be caused by compression or expansion of crystalline lattice from its unstrained condition, and this can lead to ions together or pull them apart. In either case, the local dipole moments, they are different, resulting in a change in macroscopic polarization vector P. Next, we also discussed about the strain condition changes abruptly at the hetero interface of gallium nitride, aluminium nitride, gallium nitride structure. The polarization vector changes across the interface. Lastly, the strain-induced polarization field can be used to change the local carrier concentration near the two hetero interface was discussed. Thank you.